Direct Empirical Proof of Dark Matter. This isn't a headline from a pop-sci magazine. It's the title of a peer-reviewed paper in the Astrophysical Journal, published in September of 2006. Alistair Finch of Redwood State University and his co-authors, a serious journal, a statement as strong as it gets in physics. A title like that is a rarity. Physicists usually write more cautiously. Evidence for, consistent with, indicates. Direct empirical proof is a claim to have settled the question. Finch and his co-authors believe the question was settled. But in that same paper, in the data section, not the press release, there's the collision velocity, around 3,200 kilometers per second. And a year later, another group, Dr. Kenji Tanaka and Dr. Chen, published an analysis that showed the probability of such a velocity in the standard model of the universe is 1 in a billion. 1 in a billion. Finch's paper has been cited thousands of times. The paper by Dr. Tanaka and Dr. Chen significantly less often. The National Aeronautics Directorate still uses the Arrowhead Nebula as an illustration of dark matter's existence. About the velocity anomaly, not a word in any public materials. Let's break down what's happening here. Let's start with a specific fact. March 1st. The object is called 1E0657-558, popularly known as the Arrowhead Nebula. Distance from Terra, about 3.7 billion light-years. It is a collision of two galaxy clusters that occurred about 140 million years ago. We are observing it now precisely because its light has taken that long to reach us. A galaxy cluster isn't just a lot of galaxies close together. It's a gravitationally bound system where most of the ordinary matter isn't in stars, but in the hot gas between them. A typical cluster, roughly 15% of the mass is stars, about 85% is hot gas, and, if you accept the standard model, dark matter accounts for several times more than all the ordinary matter combined. The hot gas is heated to tens of millions of degrees, more precisely, from 10 to 100 million Kelvin, depending on the cluster's mass. At these temperatures, the matter glows in the X-ray spectrum. It can be detected by telescopes like the Kepler X-ray Observatory. The Kepler X-ray Observatory is an orbital telescope from the National Aeronautics Directorate, launched in 1999 specifically to study hot cosmic gas in extreme objects. It was this observatory that provided the key images of the Arrowhead Nebula. When the two clusters collided, the hot gas, the ordinary matter, was slowed down by electromagnetic interaction, like two waves of water meeting head-on. The gas decelerated, compressed, and superheated. The X-ray images show the characteristic shape of a shock wave that gave the object its bullet name. The smaller cluster passed through the larger one and left a trail in the shape of a projectile tip. But the stars passed right through each other with almost no interaction. Because interstellar distances are so vast that in a collision like this, the probability of a direct star-on-star hit is close to zero. Stars are tiny, dense points in an enormous empty space. Two clusters of 300 to 500 galaxies each pass through one another, and the stars didn't notice their counterparts. They just went their separate ways. Here's where it doesn't add up. If the gas slowed down and the stars passed through, then the mass of the clusters after the collision should be where the stars are. That is, where they flew off to. But gravitational lensing shows something else. Here we need to explain what gravitational lensing is. Any mass warps the space-time around it, a prediction of general relativity confirmed since 1919. A ray of light passing a massive object is deflected. If a galaxy cluster is located between an observer and a distant galaxy, the light from that distant galaxy will be bent, and the galaxy in the image will appear stretched, deformed, and shifted. From the degree of deformation, one can calculate the mass of the object bending the light. This works regardless of whether the matter is visible in X-ray or optical light. Gravitational lensing responds to all mass, including the invisible kind. The Japanese Mana Ridge Observatory, one of the largest optical telescopes in the world, located in the Atacama Highlands, measured the gravitational lensing around the Arrowhead Nebula. The result? The gravitational centers of mass for both clusters are displaced. They aren't where the X-ray gas is, but where the stars are. Something massive passed through along with the stars, without slowing down in the collision. This is the observation that became the proof. The mass is not where the visible matter is. This means something massive and invisible passed through with the stars. Dark matter, a substance that interacts gravitationally but not electromagnetically, passed through, just like the stars, and carried the gravitational signature with it. Let's read the original paper. Finch and his co-authors write, "The gravitational center of mass is offset from the X-ray peak, that is from the hot gas, by 160 kiloparsecs. That's 30 arcseconds on the sky. The significance of the offset is 8 sigma. 8 standard deviations is a very high statistical significance. Physicists usually consider a result of 5 sigma or more a discovery. Hence the title, Direct Empirical Proof. The logic sounds convincing, but let's look at all the data. The same paper, the discussion section. The collision velocity. For the hot gas to get so hot and glow so brightly in X-rays, the collision velocity must be extremely high. The authors estimate it to be around 3,200 kilometers per second. That's about 1% of the speed of light. For context, the sun's velocity around the center of the Silver Stream galaxy is about 230 kilometers per second. The velocity of galaxies moving apart within a single cluster is a few hundred kilometers per second. 3,200 is more than 10 times faster than typical velocities in clusters. The following year, 2007, Dr. Kenji Tanaka and Dr. Samuel Chen published an analysis in the Astrophysical Journal. They took simulations of the standard cosmological model, the one where dark energy is described by the cosmological constant and dark matter is considered cold and non-interacting, and asked, how likely is it to find a collision in such a universe with a velocity of 3,200 kilometers per second? They ran the simulations. They examined the expected distribution of collision velocities for clusters across the entire observable universe. And they found the probability to be less than 10 to the minus 9th power, 1 in a billion. Hold on, the numbers don't add up. The direct proof of dark matter within the standard model is an event whose velocity is incompatible with that same standard model, with a probability of 1 in a billion. Both facts come from the very same object. The very same Arrowhead Nebula is simultaneously proof of the model and an anomaly the model cannot explain. How is this possible? There are several explanations discussed in the scientific literature. First, the velocity anomaly is resolved by additional unseen mass in neutrinos. Neutrinos have a very small but non-zero mass. If their contribution to the total mass of the clusters is significantly greater than commonly assumed, the collision velocity becomes explainable. This is a hypothesis not verified by direct data. Second, modified Newtonian dynamics, or MON for short. A theory proposed by the Israeli physicist Dr. Isaac Feldman in '83. It modifies the equations of gravity at very low accelerations, where conventional gravity predicts effects that are not observed. Under modified dynamics, a galaxy cluster can have different velocity characteristics. The problem: the Arrowhead Nebula is traditionally considered an argument against modified dynamics, because it also has difficulty explaining the mass displacement, though work is being done on this front too. Third, our simulations incorrectly reproduce the initial conditions. The standard model simulations are numerical calculations on a computer that cannot account for all the details of the real universe. Perhaps such collisions are possible with a specific initial configuration of dark matter that simply doesn't appear in the simulations due to limited statistics. None of these hypotheses have been ruled out. None have been definitively confirmed. The debate between modified dynamics and the standard cosmological model continues into the 2020s. Data from the Sagan Deep Space Telescope on the early universe is raising new questions. Let's examine what each of these observations is actually saying. The mass displacement, what Finch recorded, tells us that the majority of the cluster's mass does not interact electromagnetically. This is consistent with dark matter. It is a real and reproducible observation. The collision velocity tells a different story. In the standard model of the universe, which includes dark matter and dark energy, such an event is practically impossible. Such velocities require either different physics or an atypical initial configuration with a 1 in a billion probability. These are two different questions. First, is there unseen mass? The answer from the data is yes. Second, does the standard cosmological model correctly describe the real universe? The velocity data gives us reason to doubt. But in public materials, agency press releases, popular science articles, textbooks, only the first answer is present. The second is almost nowhere to be found. Names, dates, documents. Finch's paper, The Astrophysical Journal, 648 L109, September 2006. Citations, in the thousands. The paper by Dr. Kenji Tanaka and Dr. Samuel Chen, The Astrophysical Journal, 671, page 2025, 2007. Citations, significantly fewer. This doesn't mean the Arrowhead is a fabrication. It means that the direct proof is an incomplete picture. Now, who knew what, and why wasn't this publicized as loudly? The velocity anomaly has been known since 2007. This is not hidden information. The paper by Dr. Tanaka and Dr. Chen was published in open access. It can be found on arXiv and in the Astrophysical Journal. Professional cosmologists know about it, but in the public narrative it is almost absent. Why? Partly because science moves slowly and public narratives lag behind. Finch's paper was the first. It received wide coverage and it made its way into textbooks. Clarifications and contradictions come later and are covered less extensively. This is a standard asymmetry in media coverage. We've already seen this with Helios 7 and the Scorpion. The refutation appeared in the same year, but it went unnoticed. Partly because the velocity anomaly does not negate the mass displacement. The two observations exist in parallel. One could honestly say, the Arrowhead Nebula shows unseen mass and simultaneously contains an anomaly our model does not describe. But then the headline, Direct Proof, becomes more accurate as partial supporting evidence. This is more honest. It is weaker as marketing. The difference is not in the data, it's in the wording. Let's see if this is an isolated case. The Colossus cluster, Spanish for the fat one, another cluster collision, official designation ACT-CLJ0102-4901. Distance, about 7 billion light-years. Discovered in 2012 by Dr. Ricardo Vargas and Dr. Arthur Cole. Total mass, about 2 quadrillion solar masses, several times larger than the Arrowhead. Collision velocity, comparable or higher. The discoverers wrote directly in their paper, the probability of such an event in the standard cosmological model is infinitesimally small. The Colossus cluster presents a serious challenge to the standard model. From a paper in the Astrophysical Journal, 2012. The Colossus cluster received significantly less public attention than the Arrowhead. The Anvil cluster, Able 520, another collision. Its peculiarity, here, gravitational lensing shows the mass in the same place as the gas, that is, in the center. This is the opposite of what is expected if dark matter behaves as it does in the Arrowhead. One group interpreted this as proof that dark matter does, after all, interact with ordinary matter. Another found methodological errors in the observations. The debate continues. This is a pattern. Not one anomalous object, but several, with systemically high collision velocities that the standard model predicts are extremely unlikely. And each of these objects either failed to receive sufficient public coverage or was covered selectively, the part of the data that confirms the model made the headlines. The part that raises questions remained in the discussion sections of peer-reviewed journals. What exactly did Alistair Finch know when he signed off on the paper? He knew the collision speed. It's in his own paper. He wrote about it. But he didn't make a separate statement about it because it doesn't disprove the mass displacement. It creates a separate problem for the model. What did the National Aeronautics Directorate know when, in 2008, it made the Arrowhead Nebula image its photo of the week with the caption, "Proof of Dark Matter"? The paper by Dr. Kenji Tanaka and Dr. Samuel Chen had already been published a year earlier. In the Directorate's press release, there's not a word about the velocity anomaly. This is a decision about communication, not about data. Science is data. The communication of science is the choice of which data to show. Here is the direct conclusion. The Arrowhead Nebula really does show a displacement of mass relative to the hot gas. This is a reproducible observation with an 8 sigma significance. Something invisible passed through the collision without slowing down. That's a fact. But the title, Direct Proof of Dark Matter, is an interpretation, not the only one possible from the data. And the collision speed of 3,200 kilometers per second is an anomaly that the same dark matter model cannot explain with a probability higher than 1 in a billion. Both things are true at the same time. Finch's paper is an honest piece of work. The paper by Dr. Tanaka and Dr. Chen is also an honest piece of work. The problem isn't with the scientists. The problem is how one of these papers was turned into proof, while the other all but vanished from the public sphere. And here's the open question I'll leave you with. If the data simultaneously supports a model on one parameter and contradicts it on another, does that constitute proof? How, in science, not in press releases but in science itself, is one supposed to handle such situations? And if, in 20 years, it turns out that the standard cosmological model needs a fundamental correction, who will be to blame for the fact that the anomaly wasn't discussed publicly? Next time, the Triton Voyager. The Voyager Prime mission found signs of a saltwater ocean on Triton back in '96. The mission was approved in 2013. It will arrive in 2030, 17 years from discovery to approval. Who made the decision to pause, and what is the cost of that decision?